the limit comparison test, rather than doing a direct comparison between A and B, it simply asks us to consider the limit of the ratio of the two summands, the two things that we're going to sum. If that limit exists and does not equal 0, then we can make a very strong statement about the relationship between the two series. All right, so we're going to assume that this limit is L. Okay? So that means given any epsilon greater than 0, there exists a capital K such that the absolute value of AK over BK minus L is less than epsilon whenever K is greater than capital K. That's what that limit means. Okay? Now, if we look on a number line, here, this inequality sets up a window surrounding capital L. And we say AK divided by BK must lie in that window. So that means AK divided by BK is less than L plus epsilon and larger than L minus epsilon. All right, and now, since the B's are all positive, we can multiply this inequality by BK. And then, of course, because we're aware of Cauchy's convergence criterion, we're going to sum all three sides of this inequality from capital N plus 1 to capital N plus P, where capital N is some number larger than this capital K. All right? Now, this three-sided inequality is extraordinarily useful to us. Let us suppose that the sum of the B's converges. All right? Well, what that means is the sum of the B's converges. That means that I can make this tail as small as I want to just by increasing the value of capital N. And I can do that for arbitrary natural number P. All right, so I can make this as small as I want. It becomes a little bit confusing if I try to refer to epsilon again, because now I already have another epsilon. All right, it's more convenient to just think about what the statement of Cauchy's convergence criterion is that you can make this as small as you want by making capital N larger. Okay? So if I can make this as small as I want, well then multiplying by L plus epsilon, that's not going to change that. I can still make it small, right? If, for example, capital L was 300 million, then I would just make this, like let's say that I wanted to show that this was less than a given number delta. So I'm going to make this less than delta over 300 million. They're still all positive numbers. And the statement is that I can do it for any positive number, no matter how small. All right, so if I can make this arbitrarily small, then I can make this arbitrarily small, and that means that my A series must converge as well. What if my B series diverged? Now here we need to be a little bit careful. If the B series diverges, it means that I can't make this as small as I want. All right? In particular, it will mean that as P increases without bound, this is going to increase without bound. But I'm multiplying by L minus epsilon. So this will only be useful. This inequality will only be meaningful if the term on the left is not negative. If it was negative, then the inequality isn't telling me anything. I already know that this is positive and that positive numbers are bigger than negative numbers. So that's why I require the limit L to not be 0. As long as this L is not 0, I could choose this epsilon small enough that L minus epsilon is still positive. And now we're in business, right? Because if I can't make this small, this is still all positive, then that means I can't make that small. So if the B sum diverges, then the A sum must also diverge. All right? Furthermore, let's suppose that the A sum converges. Well, if the A sum converges, then I'll use this inequality to establish the convergence of the B sum. If the A sum diverges, then I'll use this inequality to establish the divergence of the B sum. So what this allows us to conclude is that if this limit gives a non-zero number, then the two series either converge or diverge together. Essentially what this is saying is that if this limit is a non-zero number, then asymptotically the two series behave in the same way. All right? Notice here this triple inequality. We're going to see that in our proofs of other convergence tests. It is a very, very useful inequality.